Hi! Good day, everyone! We are the Group 5.
And we are going to present a video presentation about two topics, that is the formation of covalent compounds.
And second is the electronegativity and polarity of substances.
Let's start!
What is covalent bonds? Overview. A covalent bond is a chemical bond that involves the sharing of electrons to form electron pairs between atoms. These electron pairs are known as shared pairs or bonding pairs. The term covalent bond dates from 1939. The prefix co means jointly, thus a covalent bond.
Introduction. A covalent bond. A covalent bond is a chemical bond that involves the sharing of electron pairs between two atoms. Covalent bonds are formed by the electrostatic attraction of their nuclei for the same electrons. Covalent bonds are mainly found between nonmetals and between metals that have the same or close value of electronegativity.
Types of covalent bond. There are three types of covalent bond: single covalent bond, double covalent bond, and triple covalent bond. Single covalent bond is when one pair of electrons is shared between the atoms. This bond occurs when two atoms share a pair of electrons to achieve a more stable configuration. A double covalent bond is when two pairs of electrons are shared between the atoms. It is stronger than a single covalent bond because it involves the sharing of more electrons, creating a stronger attraction between the atoms involved. This type of covalent bond includes 4 bonding electrons between atoms rather than the usual 2 bonding electrons that are involved in a single bond. The triple covalent bond is when 3 pairs of electrons are shared between the atoms. This bond is even stronger than a double covalent bond because it involves the sharing of more electrons, resulting in a stronger attraction between the atoms.
Structure of covalent compound. First is molecular structure. It refers to the three-dimensional arrangement of atoms in a molecule. It describes the location of the atom, not the electron. As you can see in the diagram, an example here is an oxygen. It used double covalent bond because 2 pairs of electrons are shared between the atoms.
Lewis dot structure. Also called Lewis dot formulas, Lewis dot structures, electron dot structures, or Lewis electron dot structures, or diagrams that show the bonding between atoms of a molecule, as well as the lone pairs of electrons that may exist in the molecule. For example, as shown in the diagram, carbon dioxide has 16 valence electrons. After we make a sigma bond between the atoms, there are still unpaired electrons. If adjacent atoms each have unpaired electrons, they become another covalent bond. So the carbon dioxide has a double bond. The line represents covalent bonds which contain 2 electrons. The second covalent bond in a double bond is called a pi bond.
Another type of structure of covalent compounds is molecular geometry. Molecular geometry, also known as the molecular structure, is the three-dimensional structure or arrangement of atoms in a molecule. This is the same as what have Trixie mentioned previously, which is the molecular structure, but the difference is that this structure has different shape and structural formula, that is linear, trigonal planar, tetrahedral, pyramidal, and bent.
What is octet rule? Octet rule was mentioned before by the previous reporters. Anyways, octet rule is a guideline in chemistry that states that atoms tend to bond with other atoms so that each atom has a full outer shell of electrons, typically 8. This rule helps to explain the stability and reactivity of certain chemical compounds. Atoms may gain, lose, or share electrons to achieve the stable electron configuration of a noble gas. For example, as shown right here, the atoms share electrons to make it stable.
So the second principle of the covalent bond formation is the exceptions of the octet rule. While the octet rule is a useful generalization, there are exceptions where atoms do not strictly follow it. These exemptions often involve elements with fewer or more than 8 electrons in their outer shell. So ang example sa mga elements with fewer or more than 8 electrons in their outer shell is lithium and beryllium. Examples of exceptions include molecules or ions with an odd number of electrons or elements from the third period onwards that can accommodate more than 8 electrons to their valence shell due to the availability of d orbitals.
So the third principle of covalent bond formation is the electron pair repulsion theory, or the VSEPR. The valence shell electron pair repulsion theory is a model used in chemistry to predict the geometry of individual molecules based on the repulsion between pairs of valence electrons, both bonding and non-bonding. According to VSEPR, electron pairs around a central atom arrange themselves to minimize repulsion, leading to specific molecular geometries. The theory helps explain the shapes and molecules and their observed bond angles. So this type of principle is like more connected dito sa dimension kaganina sa structure nga molecular geometry, since na-mention di ari nga electron pairs around a central atom arrange themselves to minimize repulsion. Kaning central atom is na-mention na siya dito sa geometric molecular geometry, which is nasa diari kaning planar, triangular, tetrahedral, trigonal, bipyramidal, and octahedral. So to sum it all up, this type of principle is like mauna siya ang magtabang para ma-explain or ma-determine nato ang shape sa usa ka molecule o ila ang observed bond angles.
Steps in covalent compound formation. Step 1. Electron sharing between atoms. Covalent compounds form through the sharing of electrons between two or more atoms. So, ang covalent compound na-form siya if two or more atoms mag-share og electrons. Unlike ionic bonds, where electrons are transferred, covalent bonds involve the simultaneous sharing of electrons by adjacent atoms. So, kung ang ionic bonds i-transfer ang electrons, ang covalent bonds is nag-involve siya og sharing of electrons. So, atoms involved in covalent bonding share electrons to achieve a more stable electron configuration, typically resembling that of noble gases. So, ang covalent bonding ga-share og electrons for a reason para mas stable ang ilang electron configuration.
Step 2. Determining the number of bonds. The number of bonds formed between atoms in a covalent compound is determined by the need for each atom to achieve a full outer electron shell. The octet rule is often used as a guideline for determining the number of bonds. Atoms share electrons to complete their valence shells. The number of shared electron pairs is determined by the difference between the number of valence electrons an atom has and the number it needs to achieve a full outer shell. So basically, a covalent bond is formed between two atoms sharing electrons. The number of bonds an element forms in a covalent compound is determined by the number of electrons it needs to reach octet.
Examples of covalent compounds. Covalent compounds consist of molecules formed by the sharing of electrons. These compounds often include nonmetals or elements with similar electronegativities.
Examples of covalent compounds include water, methane, carbon dioxide, and nitrogen gas. In these compounds, atoms are held together by covalent bonds, resulting in the formation of distinct molecules.
Factors affecting covalent bond strength. Electronegativity. Electronegativity is a measure of an atom's ability to attract and hold electrons in a chemical bond. In covalent bonds, the electronegativity difference between two atoms influences the distribution of shared electrons. Higher electronegativity of an atom results in a greater pull on shared electrons, creating a polar covalent bond. The greater the electronegativity difference between two atoms, the more polar bond, affecting its overall strength. Bond length. Bond length refers to the average distance between the nuclei of two bonded atoms in a covalent compound. It is a measure of how closely atoms are held together in a molecule. In general, shorter bond lengths indicate stronger bonds. As atoms come closer together, the overlap of electron clouds increases, leading to a stronger attraction between the positively charged nuclei and the shared electrons. Notable covalent compounds: water or H2O. Water is a covalent compound composed of two hydrogen atoms bonded to one oxygen atom. It is a polar molecule due to the significant electronegativity difference between hydrogen and oxygen. Methane, CH or CH4. Methane is a covalent compound consisting of one carbon atom bonded to four hydrogen atoms. It is a simple hydrocarbon and the primary component of natural gas. Carbon dioxide or CO2. Carbon dioxide is a covalent compound composed of one carbon atom bonded to two oxygen atoms. It is a linear molecule with polar covalent bonds.
So what is the importance of understanding covalent bonding? A deep understanding of covalent bonding is fundamental for advancing our knowledge in various scientific disciplines and for developing technologies that impact our daily lives. It forms the basis for exploring and manipulating the molecular world, contributing to advancements in medicine, material science, energy, and environmental science. Now, moving on to topic 2, electronegativity and polarity of substances, to be reported by Roan.
Electronegativity and polarity of substances. So what is electronegativity and polarity of substances? Electronegativity is a fundamental property of atoms that describe their ability to attract and hold onto electrons in a chemical bond. It is a relative scale developed by Linus Pauling with values ranging from 0 to 4.0. Higher electronegativity values indicate a greater tendency of an atom to attract electrons. Electronegativity provides insight into the unequal sharing of electrons in covalent bonds and the formation of polar bonds. This property is a key factor in understanding the nature of chemical interactions between different elements. Importance of electronegativity in understanding chemical bonding. Electronegativity is crucial for understanding the nature of chemical bonds, influencing the type of bond formed, ionic or covalent, and the degree of electron sharing in covalent bonds. So, ang electronegativity kay gaplay siya crucial role para masabtan nimo ang nature sa chemical bonds. It helps predict the polarity of molecules and the distribution of charge, which in turn affects a substance's physical and chemical properties. By considering electronegativity, chemists can anticipate the behavior of atoms in compounds, explain the formation of certain types of bonds, and predict the reactivity and properties of substances. Electronegativity is a key concept that guides our understanding of chemical structures and reactions.
Explanation of electronegativity and its role in chemical bonding. The Pauling scale developed by Linus Pauling is a numerical scale that quantifies the electronegativity of a chemical element. Electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. Linus Pauling introduced this scale in 1932, and it remains one of the most widely used scales for electronegativity.
Explanation of electronegativity and its role in chemical bonding. Trends in electronegativity across the periodic table. Horizontal trend. Increase across a period. Electronegativity rises from left to right across a period. This is driven by a mounting effective nuclear charge resulting from an increased number of protons in the nucleus, heightening the attraction of electrons in the outermost shell. Decreased in atomic size. Along a period, atomic size generally diminishes. The rising nuclear charge causes electrons to be drawn closer to the nucleus, resulting in a smaller atomic radius. Higher electronegativity for nonmetals. Nonmetals, predominantly positioned on the right side of the periodic table, exhibit higher electronegativities compared to metals. This reflects their stronger inclination to attract electrons, aiding in the attainment of a stable electron configuration. Vertical trend or down groups. Decrease down a group. Electronegativity tends to decrease when moving down a group. This is primarily because atoms within the same group share the same number of electron shells, and outer electrons are farther from nucleus in higher energy levels. Increase in atomic size. Going down a group, atomic size expands due to the addition of new electron shell, resulting in a greater distance between outer electrons and the nucleus. Lower electronegativity for metals. Metals, primarily situated on the left side of the periodic table, generally possess lower electronegativities compared to nonmetals. Metals exhibit a greater tendency to lose electrons readily to attain a stable electron configuration, contributing to their lower electronegativities.
What are the types of bonds? First, we have the ionic bonds. Ionic bonds are chemical bonds formed between two atoms when one atom transfers electrons to another. This results in the formation of oppositely charged ions, cations and anions, that are attracted to each other due to electrostatic forces. Ionic bonding occurs between elements with significantly different electronegativities. The atom with lower electronegativity tends to lose electrons, becoming a positively charged cation, while the atom with higher electronegativity gains those electrons, becoming a negatively charged anion. The electrostatic attraction between oppositely charged ions form the ionic bond. Common examples include sodium chloride, potassium chloride, and magnesium oxide. Next, we have the covalent bonds. Covalent bonds are chemical bonds formed by the sharing of electron pairs between two atoms. In covalent bonds, electrons are shared to achieve a more stable electron configuration for both atoms involved. Covalent bonding typically occurs between nonmetals. Atoms share electrons to achieve a full outer shell and increase stability. The number of shared electron pairs determines the strength and characteristics of the covalent bond. Examples include molecular hydrogen, oxygen gas, and methane.
Types of bonds. Polar covalent bonds. Polar covalent bonds occur when there is an uneven distribution of electrons between two atoms in a covalent bond. This uneven distribution creates a separation of charge, resulting in a dipole moment. The electronegativity difference between the atoms determines the polarity of the bond. Examples of substances with polar covalent bonds is water is a classic example of substance with polar covalent bonds. In the water H2O molecule, the oxygen atom is more electronegative than the hydrogen atoms, leading to a partial negative charge on the oxygen and partial positive charge on the hydrogens.
Polarity of molecules. So there are three types of polarity of molecules. And first is the dipole moment. So what is the definition and calculation of this dipole moment? Dipole moment is a measure of separation of positive and negative charges within a molecule. It is calculated as the product of the charge, which is represented by a capital letter Q, and the distance, which is represented by the small letter r, between the charges represented by this formula, which you multiply the product of the charge and the distance. The unit of the dipole moment is what we call debye, or represented by the capital letter D. So what is the relationship between this dipole moment to electronegativity? The dipole moment is influenced by differences in electronegativity between atoms in a molecule. A larger electronegativity differences results in a more polar bond and a higher dipole moment. So ang relationship di ani ni electronegativity o ni dipole moment is that if ang in electronegativity sa usa ka substance is larger, na ay kuan nga ang iya asang dipole moment is higher.
What are polar molecules? Polar molecules have an uneven distribution of electron density, leading to a separation of charge. This occurs when there is a significant electronegativity difference between the atoms in a molecule, resulting in the formation of polar bonds. Examples of polar molecule. Water or H2O is a classic example of a polar molecule. The oxygen atom is more electronegative than the hydrogen atoms, creating a dipole moment and resulting in a partial negative charge on the oxygen and partial positive charge on the hydrogens. Nonpolar molecules. Nonpolar molecules have an even distribution of electron density, and the electronegativity difference between atoms is minimal or non-existent. This can occur when atoms of the same element are involved or when the polar bonds in a molecule cancel each other out. Examples of nonpolar molecules. Diatomic molecules like oxygen and nitrogen are examples of nonpolar molecules. Additionally, carbon dioxide is a linear molecule with polar bonds that cancel each other out, resulting in a nonpolar molecule.
Factors affecting polarity. Molecular geometry. Molecular geometry refers to the three-dimensional arrangement of atoms in a molecule. It considers the spatial arrangement of atoms and the bond angles, providing insights into the overall shape of a molecule. So this is the impact of molecular geometry on polarity. The molecular geometry of a molecule is a crucial factor in determining its overall polarity. Even if individual bonds are polar, the molecule as a whole may be nonpolar if the polarities cancel each other out due to the arrangements of atoms. Examples of different molecular geometries. Examples include linear geometry, carbon dioxide CO2, trigonal planar, boron trifluoride BF3, tetrahedral, methane CH4, and bent or V-shaped water H2O.
One of the factors affecting polarity is symmetry and asymmetry. Symmetry plays a crucial role in determining molecular polarity. Symmetrical molecules tend to be nonpolar, as any dipole moments created by bipolar bonds are cancelled out. In contrast, asymmetrical molecules may be polar if there is an even distribution of change. Examples illustrating symmetry and asymmetry. Symmetrical is a carbon tetrachloride CCl4 is a symmetrical tetrahedral molecule where the polar CCl bonds cancel each other out, resulting in a nonpolar molecule. The asymmetrical, one of the best example is ammonia. NH3 is a symmetrical molecule with a trigonal pyramidal shape. The electronegativity difference between nitrogen and hydrogen creates a net dipole moment, making it a polar molecule.
Water molecule. Water molecules are made of hydrogen and oxygen atoms, in the definite proportion of 2 hydrogens for 1 oxygen. Hence, a molecule is the smallest subunit of a compound, while an atom is the smallest subunit of an element. Explanation of water's polarity. Unequal sharing of electrons make water a polar molecule. This means that electrons spend a bit more time at the oxygen end of the molecule. This makes the oxygen end of the molecule slightly negative. Since the electrons are not near the hydrogen end as much, that end is slightly positive. Significance of water's polarity in biological systems. As a result of water's polarity, each water molecule attracts other water molecule because of the opposite charges between them, forming hydrogen bonds. Water also attracts or is attracted to other polar molecules and ions, including many biomolecules such as sugars, nucleic acids, and some amino acids.
So another type of case study is the carbon dioxide molecule. So what is a molecule of carbon dioxide or CO2? A molecule of carbon dioxide, CO2, is made up of one carbon atom and two oxygen atoms. Carbon dioxide is an important greenhouse gas that helps trap heat in our atmosphere. So what is the explanation of carbon dioxide of so what is the explanation of why does carbon dioxide lacks polarity? Carbon dioxide is symmetric and the pull of the two oxygen atoms on the carbon's electron cancel out. So it is non-polar molecule with polar bonds. So ang hinungdan di ay nga nung nag-lack of polarity ang carbon dioxide is that because ang kuan siya symmetric, which is kani nga word is ay na-explain na previously sa akong mga ka-group mates, and this is the ang katong pool sa duha ka oxygen, since am sa duha ka oxygen atoms o isa ka carbon atom, mo to siya ang hinungdan nga nung ma-cancel out ang electron sa carbon, resulting nga gamay ra dayon ang iya ang polarity. So, this carbon dioxide is non-polar, but naagyapon siya, it is non-polar in polar bonds. It is a non-polar molecule in polar bonds. So, what is the implications for its physical properties? Carbon dioxide appears as a colorless, odorless gas at atmospheric temperatures and pressures, relatively non-toxic and non-combustible, heavier than air, and may asphyxiate by the displacement, and is soluble in water.
Goodbye and thank you for listening.
We hope that you have learned something from our video presentation.
Bye.